Alrighty. So, believe this is more or less week 10. Um, just about around, right? So post midterm, post spring break. This is when we get into some of the synthesizing of knowledge from what we've learned. I mean, in general, how this class is structured is you learn a lot of things, a lot of individual concepts leading up to the midterm, and then post midterm, we try and take that and put it all together. So now we're not really learning new stuff. We're kind of taking the stuff that we know and building that into more advanced constructs. So that's going to be the theme for the next few projects. In previous semesters, what we've done is we've released projects 5, 6, 7 all at once. We probably won't do that this semester because we actually can afford to give ourselves a bit more time than that. So we'll see how it goes. We're going to try and make this kind of easier on you guys, just adjusting the schedule as we go semester by semester. So hopefully this works out a little better than our previous systems. Okay, that being said, let's go ahead and get started. Like I said, the slide deck is a little older, but I really like the diagrams, so I'm kind of keeping at it, at least for this semester with this one. But yeah, ROM and assembly. So, announcements real quick, projects 5, 6, and 7. We'll talk about those, and then here's a quick overview of the things we're going to talk about today. I think this is one of our cooler lectures. All right, announcements. Okay, well these are some old slides here, but Project 5 will be released soon, and actually it's neat because Project 5 is a bit of a heavier one, right? Um, Project 6 will be a little bit lighter, and then Project 7 will be not as heavy as Project 5, but you know after this it's kind of smooth sailing from here on out to the final project, which is really not too bad. But these next three projects are not so much tailored to new concepts, but instead to the actual project that you'll be doing. So, you know, hopefully this will pertain a little bit more to the actual work that you'll be implementing. At least giving you some background on you know, what exactly you'll be doing. Right, so here's an introduction and some background to what we'll be talking about. So we've built the ALU, right? The whole thing. It's kind of already finished now. That's the brains of the operation. But now we need to do a few more things to take this from just a calculating circuit to an actual computer, right? So to remind you, we've got all this functionality, this add, subtract, multiply, XOR, you know, logic gates, all that business, bit shift. It's all there. It's all good to go. But our problem now is providing this circuit with the right input and you know piping that output to somewhere where it can be stored in a way that'll make this rather a computer, not just a calculating circuit. So specifically, we need ways to do a few things, right? We need ways to store our programs, that's one thing. We need ways to interpret those programs, and of course, ways to execute data and store data for those programs while they're executing, right? This all is computer architecture stuff. It may seem familiar if you're kind of into that business yourself, but really what we're doing is we're designing, at this point, a computer, right? And we have quite a bit of freedom in terms of how we do something like that. But let's go ahead and kind of reason it out ourselves. In that we're going to be using, you know, the digital logic circuit theory that we kind of know already to build circuits to address all of these problems, right? So let's go ahead and begin with one thing. A little bit of an overview of what our projects will be covering, right? Number one, we've got ways to store programs. That'll be in ROM, right? Read-only memory. This is kind of interesting how we address this problem, so stay tuned for how we actually go through it. But also we need ways to interpret those programs, right? So that kind of paves the way for our own special brand of assembly. It's very simple, the assembly that we've created, called 389E assembly. And that'll also be project 5. Additionally, we need ways to execute those programs, right? So that's why we've got a project 6, which really introduces you to a program counter and a clock. If you've taken Herman's 216, you'll be kind of familiar with how this circuit sort of works, because I think his like second or third project, at least when I TA'd for him, and the semester before that was this like coffee cake thing or mathlon, or he calls it different things. They're just based on whatever processors are like kind of out. in the past. They're just based on old processor names. But it's essentially what we're building here. We're kind of trying to emulate a computer at the lowest level, right? Which is why we're going to spend some time, building a program counter register, building the proper adder circuit to increment that at every cycle, right? And move from line by line in our code. Okay, so far we've got ways to store programs, aka the code that will execute in ROM, right? Built of our own 389E assembly. We have a program counter, which allows us to kind of step through those programs. And of course, we are going to build ways to store data for those programs while they're executing, right? In other words, I say store data and all that business, but the words that should be familiar here are like registers or, RAM. We use the terms kind of interchangeably. I'm aware of the differences between the two. If I were you, I would just think of these as registers, right? We need registers for our program while they're executing. We've got a finite amount of them. And here we'll be actually building these registers in Minecraft and reading and writing to and from them as our program executes, right? So again, I want you to think of like, if this is a little confusing, think of like the most basic assembly programs you've written in like 216 or any of your other classes, right? That's the kind of program that we're looking to support, where we have, perhaps a finite amount of registers. We've got, perhaps some values starting in a few registers, and we want to end up, I don't know, doing some operation to them and landing them in that register at the end, right? So very simple stuff. That's basically the extent of what our computer is going to be able to do. What we're basically doing is we're taking this ALU and saying, okay, let's build some constructs around it to make that ALU's calculations meaningful. That's what we're building here, right? Okay, I'm going to real quick just check to see if there are any lecture questions. Actually, I'm going to get my phone so we can take a look at lecture questions while we're going through this. Right. But yeah, at any point during this, if you have any lecture questions, feel free to throw them at the lecture questions chat. We'll be taking a look as we go. All right, moving on. Here's the problem that we want to solve, right? This is what we're trying to address with this whole sort of construct, and that is we're understanding that we need a way to store our programs and we need a way to interpret our programs, right? So let's go ahead and build some guiding questions to help us answer these, right? First few, how exactly will we represent our programs, right? And how much space will we need? These are very important questions in that this is going to kind of dictate the type of architecture that we're building and the physical limits of what we're building, right? So once we figure out how we'll represent our programs, i.e. like what are we going to do? Are we going to make them series of ones and zeros? Are we going to make them some weird form of assembly, right? Once we figure out how we represent them, we can easily develop constraints in order to store them, right? And once again, I keep making allusions to Herman's 216 because he sort of kind of guides us through that with his whole thing on opcodes and assembly and stuff like that. So that's a good introduction to stuff that would otherwise be looked at in like 411 or something. But that's kind of the path that we're trying to go down, right? So in other words, storing the structure of our computer programs, right? So once they're stored, we can easily tackle how we'd help our computer interpret them, right? We'd build architecture to decide what to do. So, first things first, let's go ahead and figure out storing first. So far, we've designed add, subtract, multiply, and other 3-bit operations. Where else have we seen basic operations like this, right? So basically what I'm trying to get at in this slide is assembly, right? So let's take a page out of the first few programmers' books and say that we are going to write some stripped down, non-pipeline, no fancy business version of assembly, right? So for this project, we will be using a 14-bit version of assembly created by the Divine themselves for use in CMSC389E, right? In other words, I'm saying that we need 14 bits to be able to store each instruction in 389E assembly. That's the main goal here, right? And it's interesting because we are building a computer that does not use 14 bits, right? We will only be using, like 3 bits or so to represent just about everything else on this computer. add, subtract, multiply, and otherwise work using 3 bits. However, we can't get away with using just 3 bits for each assembly instruction. That's not going to work. That gives us like, a maximum of three ones and zeros. That's asinine. That's not going to let us do much in the way of logic. So we've decided to kind of step around this restriction and say, okay, everything, including all the data that we're storing, all our quote-unquote registers, will be 3-bit. That's fine. But we're going to have a special chunk of memory that's 14-bit, right? 14-bit for each, line of code, let's say, that is going to store each instruction for 389E assembly. This is a little unorthodox, but it actually simplifies a lot of the problems that would be caused if we were to either write 3-bit instructions or be able to support, a much higher amount of bits for instructions. And thusly we'd have to support it in other operations as well. So this is the easiest way to go, basically. So TLDR, our operations are 3 bits still, but the only thing that's going to be stored in 14 bits are the actual instructions that we're going to be interpreting. Okay, I've given you some background here, but let's talk about how much space we'll need, right? Like I said, we've got a 3-bit computer, but our assembly will take more than 3 bits to store. And this is just a little bit more of explanation on why we're doing something, or how we're doing something like this, right? So most computers, including the one you're looking at this lecture on, will store their programs in writable memory so that they can be rewritten by the CPU. But I'm saying that we can drop that functionality for now. We're not going to design our programs in such a way that our computer itself can edit those programs. So hopefully that makes sense. For example, when you're writing code on your machine, that's not hard-coded business. You can be typing it out in an editor and pressing compile and run, and your computer compiles and runs code that you have written on it yourself, right? What we're doing is, as we're building our computer in Minecraft, keep in mind that that's the analog to putting the actual hardware together in real life. We are literally sort of soldering the code to that computer. We are building it manually ourselves, saying that, okay, even if the actual user of this computer can't edit the code that I'm putting in, the user can still execute that code, right? In other words, we don't need the ability to manipulate the bits in the instructions that we're writing. We are going to hard code all of the, quote-unquote code, the instructions for our computer, and that actually allows us to do all that in like 14 bits and not have to worry about manipulating those bits at all. So that's the deal behind that. So then why ROM, right? And we talked about different types of memory, I would say a few lectures ago, right? Before the midterm. Quick overview again. ROM is just read-only memory, right? It's hard-coded, soldered to the motherboard, all that good stuff. ROM is a pretty good candidate for this. Remember, our computer has a 3-bit architecture, and we didn't pick read-only because it was optimal. We picked it because it's the easiest to build. In other words, there isn't much instruction you would actually be able to store in 3-bit sized memory, right? For example, we've got, 101 is an example thing that we could store in 3-bit sized memory. I mean, how many programs are we going to be able to write with 3 bits per line, right? What are you going to say? Like if there's a 1, instead of a 0 on the first line, it's like a store instruction instead of a load instruction. Very quickly you'll find out that there is no flexibility at all in a language that is so strictly defined. I mean, you could go the extra mile and be completely asinine and put a lot more load on our actual interpretation architecture, right? And say, okay, we could have like 3 of these 3-bit lines in a row represent one actual line of code. And although possible, it's just so much more work to interpret something like that in order to keep this, simple and fairly understandable, we're going to work around this limitation, right? It turns out that, this sort of issue is much more easily addressed on actual computers because they use things like 32 and 64-bit architecture, which have plenty of room for these instructions. For example, MIPS has 64 bits available for any sort of, register, that sort of thing. I mean, a bit of a sidetrack there, but when you have these larger amount of bits to play around with in your architecture, if you're like a 32-bit or a 64-bit architecture, you don't have to worry about problems like the one we're worrying about here in our 3-bit architecture. So that's our workaround for lines of code. So again, a little bit more, right? Our pro is that we can store a lot more data in those 14 bits, but we'll have to manually edit our computer to change the programs. Now, this is no big problem for us because we are building this in Minecraft, right? If I propose some sort of schematic like this for a physical, hardwired computer, people would call me an idiot because they'd say, why would you ever think that in order to change the program on this computer, we would want to go ahead and like solder some new stuff to the, I don't know, to some sort of board, right? So for our computer, even if we want to change our programs, all we have to do is go in and break a few blocks and put some more down, right? It's that simple. That's how we're going to be building our programs. We're going to be coding by putting down blocks. Now keep in mind that ROM, not all is lost with ROM. There are plenty of systems and digital circuits that you would much rather just not have the code be editable at all. Like, when is your hairdryer going to receive a patch, right? Hopefully not. I mean, I know that some had the tendency to like explode and they were recalled, but that's beside the point. In other words, it's still doable to do, to code on ROM, but it's doubly useful for us because it's very easy to go into that ROM, that hardwired pre-built ROM, and instead of using our computer, right, our Minecraft computer to change that code, we will just use our blocks. We're gonna go ahead and break a few blocks, put them down, and boom, your code is quote unquote changed. So that's the good stuff. That's why we use ROM. I mean, it just makes things 10 times easier for us, and we just have to mess with a little Redstone if we ever want to edit our hard-coded programs. Okay, let's think about representing an instruction, right? In order to store our assembly-based instructions, I'm going to go ahead and arbitrarily say we need 14 bits for each instruction. Why? It's a magic number. It's excellent. We'll call 14 bits one line of instruction. And in here, we've got a lot of specifications, and you'll read more about this in the project spec. We've got some more detailed stuff coming out this evening on the Project 5 spec that'll actually explain, okay, the first 4 bits are used for opcode, these 3 are used for register 1, these 3 are used for register 2, and these 4 are used for, like, I think, overflow or, like, some sort of immediate, something like that. Off the top of my head, I don't remember instantly, but it's something like that. Long story short, we will be needing 14 bits or so for each instruction. So hopefully that's somewhat familiar. I know Herman's project, again, was very much in the vein of showing you, this bit is for opcode, this bit is for R1, this bit is for R2, that sort of business. And if you've taken 411, or if you're familiar at all with like MIPS or anything, again, 216 switches assembly languages, so it's kind of hard to make sure that I'm relating to everybody here. But if you are familiar with how assembly is represented on a binary level, that's essentially what we're trying to emulate here, right? Only caveat is we are doing it in a much more simple way. There's no load store business, nothing like that. We're not accessing main memory or anything like that. We are simply screwing around with a few registers. And also, additionally, there is no heap, there is no dynamically allocated memory. Why? Because that would be a whole another class of Minecraft stuff to implement. So let's just keep it simple and call it what it is. We're going to be just implementing a few registers, and we're going to be writing assembly that manipulates just those registers, right? Turns out you can do plenty of stuff with that as well. Cool. So, digression finished. It is 14 bits for each line of assembly, right? Now, keep in mind that we remember what bits are. Bits are just ones or zeros, right? And our conclusion is we need individual lines of read-only memory with 14 bits in each line. This will allow us to store programs for our computer, so 14 ones or zeros, right? So keep that in mind. Think of it this way. This right here, this boy is a line of code, and it's composed of ones or zeros. That's all we're going to need. Okay, so is space the reason why people use ROM? Like I talked about earlier, not necessarily, right? Most functional computers don't have this absurdly small space requirement, so on and so forth. I've already kind of given a little bit of a talk about this, but there is a cool little example here about the BIOS. I'm just going to kind of gloss over it for now. You can totally read it later. I just want to add that these slides are a lot thicker than the usual slides. Back then, I used to design these slides such that you could just look at them with no context during lecture. I mean, like, with no context from lecture and still kind of gain a lot of stuff from it. But I realized afterwards that it would kind of make the actual class bit a little bit more, I guess, contrived. You'd have to spend a lot more time looking at the slides each. But I'd like to point out that these slides are definitely built in such a way that, you can totally take a look at these later and kind of glean the information. Another reason why I decided to include this for this week, just because I feel like conceptually this is a lot more than what we usually talk about. So that being said, I'll just go ahead and skip over this slide. We talked a little bit about it already. Now let's talk about the structure of our read-only memory. Okay, so long story short, we need 14 bits. How are we going to put those together, right? Storage in Minecraft is how. Now that our memory has to be read-only, we're all set. Remember that simple read-only memory circuit that we looked at earlier? This will be even easier. A long time ago, right, we built that like simple, gate with like 2 NOTs, 2 inverters, where the torch you'd have something turned on. Very simple read-only memory, right? By eliminating the need to set and reset our memory, we've reduced it down to a highly simple concept. In other words, we just need to specify, hey, is this on or off, right? So a 1 can be as simple as a redstone torch being in a spot, and a 0 can be as simple as a redstone torch not being in that spot. So suppose this was our beautiful line of code here, built in 389E assembly. Cool stuff, not a problem. In fact, to represent this in Minecraft, all we really need to do is have 14 blocks right next to each other, and have torches where there are 1s, and no torches where there are 0s. And that's how we bridge the gap, everybody. That's how we're kind of doing this, right? Each line of code is going to literally look like this. I think that's kind of neat. You can literally be writing code just by putting down an arbitrary number of torches. So that's how we're building our code, right? And if that seems somewhat simple to you, remember, this is just the structure of a computer program. The interpretation is the architecture that we're going to build to say, hey, let's check these first 4 bits, right? Using some sort of logic gates in Redstone. And based on what these first 4 bits are, we'll decide what the opcode is. So we'll say, oh, you know what? That's this right here is an add instruction, right? And then your architecture will go in and say, okay, this is register 1, this is register 2, and do all this fancy business based on that, right? But for the structure of our computer program, this is all that we need, right? Torches where there are 1s and no torches where there are 0s. So again, feel free to throw stuff in lecture questions if this is getting a little bit weird. We're trying to keep it all together, so don't be afraid to ask if this is a bit of a toughie. So we can actually figure out what each line is saying by running some redstone wire under these blocks, right, in order to pick up the output of the torches. And Ashwath has got, I think, so he is feeling a little bit under the weather at the moment, but I believe he's got a video that he wants to come out with that'll really give you a Minecraft explanation to this sort of thing, right? So we can figure out what each line is saying by running some redstone wire underneath the blocks, just in order to pick up the output of the torches, right? Notice that the ones under the torches are on and the ones under the no torches are off, right? Pretty commonplace stuff. This is more of a diagram than anything, but the Minecraft analog to this is just like, it's basically how it looks right now, right? Very simple stuff. So now we have an idea of how to write a line of our 389E assembly. In other words, we just put down a bunch of torches in a particular layout, and boom, you've written some assembly, baby. So forget about the actual rules of assembly, but for now, don't worry, you'll kind of get to that in the project, and believe me, it's like a much simpler version of the 216 assembly. It won't be too much trouble. Let's just be pleased with the fact that we figured out how to represent a line of 0s and 1s within Minecraft. Excellent stuff, right? Wasn't too bad, we nailed it. Here's another question. This is just one line. Let's expand this. How can we represent different lines of code, right? And I want you to think about this by your lonesome for a second, right? Kind of imagine what sort of architecture we'd need to put in place in order to expand this, to look at multiple lines. Would we keep it on, multiple different lines of redstone? How would we switch between lines, right? And again, this goes very well hand in hand with some other stuff that we've learned this semester, right? Where we can, here's your big hint, how will you enable only one line at a time to be read, right? If you have like 16 lines and you want to say, okay, give me line 1, okay, give me line 2, okay, give me line 3, so on and so forth, right? How can you build a sort of digital logic construct to request each of these individual lines separately, right? Because keep in mind, this is not going to just be sequential. You might go line 1, 2, 3, jump instruction, line 7, right? So you need a way to be able to say, okay, circuit, I need line 7, and then the circuit says, okay, sounds good, and it sends it to you. So think about that. I kind of gave you a sort of poke in that direction, and it is very similar to one of the circuits that we've already built this semester. So think about what we've already built. Hopefully that's floating around in your mind, but I'm going to go ahead and throw the answer at you. Wait, what did I do? Oh, okay, all right. Yeah. So while we're getting there, I mean, it's quite simple. We just make more lines, first and foremost, right? We just build multiple lines of code just like this, and you can see that they are, they vary and all that business. They've got different opcodes, they've got different register references, that sort of thing. And we've got a guide, right, to translate these ones and zeros into actual assembly. Like this will be like add. Again, this could be like add or something. This could be, I don't know, XOR. I'm just making stuff up, right? Obviously, these aren't the real instructions. But yeah, no, it's pretty simple to translate this once you get into ones and zeros. Then you can translate those ones and zeros based on opcodes and such, and register numbers, etc. So let's talk about interpreting this in Minecraft, right? And I kind of touched on this already with the whole, requesting line by line. But let's think about it, right? Let's say we can store multiple lines. We have a new problem. If we wanted to interpret this code, how can we detect what each line is telling us to do? We can see right away that simply running wires underneath every line using a bus won't work at all. We'll just get all the on bits at once. You can see here this visual representation. If we have 3 lines of code and we have redstone torches like this, we're just going to get the only bits that are on, right? You can see here that even though this was on here and this was off here, we're still getting red coming down this way, right? Down this wire. The diagram's a little bit garish, but, it's kind of hard to use LaTeX sometimes. But you can see here that this is thoroughly useless. I mean, we're getting all of the on bits, so we're not getting any actual description at all from this bad boy. So we're going to have to add some more digital logic magic in order to make it so that we can request individual lines, right? And not just all the lines at once, because that is quite useless. Now, we need a way to get the data from one of these at a time. Is this reminding you of a circuit that you've built before? Think about where you've seen long parallel rows of blocks with torches, right? That's my final little hint there. And if this hasn't kind of poked you in that direction already, this is indeed the decoder, right? We're going to be using a binary to decimal decoder. We'll explain why in a second here, right? So binary to decimal decoder. Let's call this the decoder. I've extracted it down to an orange rectangle because I'm lazy and I hate diagrams. But we can see that it's got an input, right, in binary, asking for the values of a certain line of code. In other words, this decoder, this binary to decimal decoder is saying, okay, give me what you want binary. So I say, okay, decoder, I want 1 0, right? That is 2. So then decoder says, okay, you want line number 1 0? No problem, right? And remember, we 0 index, so this is line 0. Line 1, line 2. That's just like a personal, like a choice that we consciously made here, the 0 indexing. But yeah, if we say, coming in here to this decoder, we say, okay, I want 1 0. This thing is going to say, okay, sounds good. And it's going to decode and tell us it's going to only keep these on, right? And give us the response for this line of code. Line number 2, 0, 1, 2, right? So that's at a very high level how that works. And of course, why a binary to decimal decoder? Well, you don't know this yet, right? Why? So you might be wondering, okay, why don't we just give it like, the number in actual decimal form? We say, okay, 0 for 0, 1 for 1, 2 for 2. Why wouldn't we just do that? Now, the thing is, our circuit basically says, here's the line number that we're currently at in binary. Can you get me the data stored in that line of code, please? And then the decoder says, okay, sounds good. Here's that line of code, right? Now, what we have to remember is that we don't want to request from the decoder and what's convenient for us. We have to understand what our circuit is going to be that is going to actually request from this decoder, right? And it turns out, well, that's it. Well, yeah, it turns out that that processing bit, right, the program counter, which tells us what line we're at, is going to be in binary itself, right? It's going to be a 3-bit register that represents our line number, right? And it's going to tell us, hey, we're at line 4, and it's going to say that in binary. So we can pipe that output directly from the program counter to the decoder for our actual ROM. So in a very simple way, we don't need to convert anything. Like I talked about before, computers really like talking in binary, right? So having us be able to take the binary line number and request it right from the program counter register is pretty valuable. And that's why we're using a binary to decimal decoder, right? We're basically saying, okay, program counter, what line are we at? And program counter says, okay, here's the line number in binary. And then the decoder goes ahead and takes that line number and gives you the code that's there already. So that's the deal with that. So now we can safely say that we know how to do two things. First and foremost, we can store multiple lines of 389E assembly code using redstone torches and blocks, which is excellent. And second of all, we can use binary to decimal decoding to, given a line number, produce the appropriate corresponding line of code that is stored in our ROM. Now that's excellent news, because now all we need to do is interpret those lines of code, right? And we're home free. So great stuff, right? We've worked through the basics here. We're saying, okay, give me a line number in binary, and my circuit will go ahead and say, all right, I'm going to give you the code for that line number, and it's going to go ahead and run it down, a series of redstone signals. So here's what we got so far, right? This is a cool diagram, basically, of what I just said. We ask for a line of code and get 14 parallel signals, right? I used this terminology before in the multiplexer lecture, right? Representing 14 bits of 389E assembly. And this means exactly what it sounds like. It's just parallel signals, right? Parallel wires. So here's the step-by-step, right? We request this line. We say, okay, we want whatever's at this line. Then our circuit does some decoder magic, right? Right, let's say I say, hey, I want line 5, right? Our circuit will say, okay, sounds good, and it's going to give us this business right here. All of these lines, right? 14 parallel signals for us to work with. And in fact, that is where we're gonna kind of stop off today in a way, right? So how are we gonna actually interpret these 14 parallel signals of 389E assembly, right? In other words, what will we actually do with the signals that we have? Now that is where our journey ends for now, right? The answer lies in the project specification for Project 5. I'll talk more about the actual work you have to do to interpret the assembly lines using an actual circuit once we finish the rest of the pieces of the puzzle, the program counter registers. In previous semesters, we've sort of distributed the actual Minecraft stuff to do this whole interpretation business, right? It takes a while to code it out. So we might end up doing the same thing this semester, in which case, your Project 5 is usually not too bad. It is just on the topic of, actually, I'll save it for the next slide. This is the last slide. But yeah, this is where the journey ends for now, right? We are going to, in P5's spec, kind of see, okay, how do we take these 14 bits and represent them in actual assembly, right? And once you do that, we get on to what we're doing in Project 5, which is meant to familiarize you with the highly simplified but super radical version of assembly that we'll be working with for our project. So that's what Project 5 is, and I'll go ahead and talk a little bit about that now, I guess, since Ashwath isn't here. So pretend my voice is a lot deeper as I go into this next segment. Okay, so Project 5, right? Actually, first of all, if anybody has any questions on the past few bits, feel free to drop them in now, right? We can go ahead and review a bit. And I think after we talk about Project 5, I can go ahead and let you go a little early. That's also totally cool. But yes, I'll take this moment to take questions, and feel free to throw them in here as I talk about Project 5 as well. But yeah, so basics for Project 5. This is a bit of an unorthodox project. It's different from the ones we've done before because, gasp, it's not in Minecraft. But fear not, we have written essentially, well, somebody else has put together a Java runner um, that compiles and runs some pretty basic rudimentary assembly, right? That your job will be to code, yourself, just in plain assembly, and the problem is not hard. It's just literally saying, okay, given a limited number of registers, right, and a project spec. Ooh, excellent voice correct there. A limited number of registers and a project spec, code up an exponentiation algorithm using assembly, right? Basically, all that's available to you is, I think it's like only addition, like you don't get multiplication or something like that. Or I think, oh, actually, no, it is like multiplication is available. It's basic, it's very simple, is what I'm trying to say, right? Yeah. So it should be quite simple. I think even if addition is available, I keep forgetting which one is. But it's just an exponentiation algorithm in assembly. It's meant to familiarize you with the actual assembly language itself. Honestly, the autograder we've got for it is a little buggy sometimes. So we found that if somebody produces a solution that we don't expect, it sort of chokes sometimes. So if you run into problems with this project, or if you just can't get it to work, or if the assembly is just hard to beat into your head, just no worries. Please, this part of the semester, or this project specifically, is when a lot of people will just schedule office hours. So I'm kind of good. My exams don't start until a few weeks from now, so I'm good to answer questions and set up office hour appointments, and so is Ashwat, right? So please feel free to message us to set up office hours if you want in advance. That would be, we can't guarantee same day appointments, but if you tell us day before or something like that, we can totally clear up some time and make it happen. So please let us know, right? The project spec will be out either later tonight or tomorrow at the latest, right? It'll also be on the course website. And like I said, it'll be slightly different. So if you have any troubles setting up the project runner, or if you have any troubles actually writing it yourself, I'm a 216 TA, so I'd be more than happy to help you reason out the assembly yourself. So please hit me up. I don't want to speak for Ashwath, but I'm sure he'd be happy to help too. And that is the summary of Project 5. So basically, you'll get a lot more of an introduction to the assembly that we'll be talking about in that Project 5 spec. So that'll come out soon. And that's that. We've got a few minutes now as we round this out, so I'll take Project 5 questions and also questions on the midterm exam. Just in general, did we think that midterm exam was okay? We make that, try to make that kind of, oh dear, decent as possible. Am I still on the Discord? Oh yeah, okay, I'm still here. That's good, alright. In general, any questions on the midterms? What do we think of it?
The storytelling was fantastic.
Excellent, thank you. That's a fan fiction of my own design. So
I was really on the edge of my seat the entire time.
I appreciate it. Excellent. Solid. I was thinking of changing it for next semester, maybe writing in some of the students from this semester, but I don't know if I'm allowed to do that. I don't know what the university rules are for that. But thank you. Excellent stuff. No hard feelings to David Mount or anybody else I mentioned. I think he was just the first dude who came to mind when I was writing that. Or he was the interim department chair when I was writing that sort of deal. So I saw a question about auto grading on the midterm questions. No worries about that. What I do is I go in after the auto grading, and while I'm manually grading, I make sure that the auto grading hasn't screwed itself up. But obviously it is a lot of exams to look through. So if you see an error in your final grade, there is the regrade deadline is open up until the end of the semester. Just be hey, I think you screwed up my midterm grading. So if you want me to go ahead and take a look, feel free, just hit me up, and I will go ahead and dig through it. I think Ashwath is also taking on some of the grading this semester, but it's fairly universal, so hit either of us up if you see what you think is an error with your grading. Keep in mind, right now, you won't see your final grade. I think what Elms does is it takes the auto-graded questions and sums that for your final grade, so don't worry, it's not bad. Also, if this exam screwed you up, which I hopefully did not, because I did include a solid amount of extra credit points just to keep it from being too deadly. If it did, I mean, we've never had to curve this class before, but we're not here to like screw you guys up or mess up your GPAs or anything. So, that's I'll leave that open to interpretation. Just it shouldn't cause any problems, right? It's just meant to sort of gauge to see, are people kind of picking up what I'm putting down. All right, that being said, if there are no questions on exam grading or anything like that, I'll be here for a little bit if you want to ask any personal like questions about exam grading or anything like that. Private questions, I will be here after lecture, so you can stick around for a little bit. I'll be here for like 10 minutes or so. But other than that, that's lecture. Thanks so much for coming, everybody. And Project 5 spec will be out later today or at the latest tomorrow.
Thank you.
Yep.